Welcome to Study Loop.
So here we are given a figure that shows a thermodynamical process that represents a system, a gas system that is going it is coming to a change of pressure, where the pressure starts at some given value that is given here, and then the heat is added into the system, and the pressure changes, the pressure doubles, but the volume is constant at all times. So this is an isobaric process. And for the part A of this problem, we need to solve for the work done in the process, but between points A and B on the figure. So since the volume is constant during the whole process, where there is constant volume, the work done is being always zero, since from the definition of the work, we know that it is an integration from V1 to V2 PV times differential of the volume. And if initial and final volumes are equal, or if volume is constant, that implies that the integration will be always equal to zero, and therefore the work will be always equal to zero. So for this part A, the work AB is going to be equal to zero. Next, we have the part B. For the part B of the problem, we should start by applying the ideal gas law. So it's going to be, of course, pressure times volume equals nRT. And we know that the right hand side, know that the volume is constant. We know that number of moles is constant, and this is a gas constant. So pressure and temperature are directly proportional, and this proportionality can be observed from this formula. Now, to be specific, as the pressure increases, the temperature increases, and this is due to the fact that it is all happening at a constant volume. Since there is no expansion of the gas, all of the molecules of the gas need to be faster, since their pressure is increasing, so their kinetic energy is increasing. And since temperature represents an average kinetic energy of a molecule of the gas, therefore, since all molecules need to move faster, their kinetic energy needs to increase, so the temperature will increase with the increase of the pressure. And since at the point B, the pressure is 2 times larger than at the point A, which we can, of course, write down as PA is actually, we'll start from PB equals 2 times PA. Since pressure is directly proportional to the temperature, therefore, anytime we have this kind of direct proportionality, if one variable, like pressure in this case, goes 2 times, 3 times, 4 times of its magnitude, then its proportional variable will go also 2 times, 3 times, or other times, depending on how many times it is going to be increased. So since we have 2 times, the pressure is 2 times increased, therefore the temperature at the point B will be 2 times of the temperature at the point A, and this is the solution. So temperature at the point B is going to be equal to 2 times temperature at the point A. This is all from the law of proportionality in mathematics in general. So, and this is a specific solution for this question. And for the point C, now here we need to address that we know that the work done from A to B is zero. So according to the first law of thermodynamics, when we add heat into the system and there is no work done, all heat will be converted to internal energy of the system. So delta U equals Q minus W, and since W is going to zero, therefore it implies that the internal energy is equal to Q. Now we know, and we are given in the problem, that this equals 700 joules. So since all added heat goes into internal energy, if we consider the internal energy at the point A of the system and call that at the point A, the internal energy is UA, and at the point B, we say that the internal energy is UB, the relationship will be, again, at the UB. Since UB is the final point of this thermodynamical process, the difference between UA and UB will be exactly equal to Q. It will be exactly equal to the heat added. Therefore, the final answer to the relationship between these two is that internal energy at the point B is equal to internal energy at the point A plus 700 joules, which is equal to the heat that is placed into the system. And by this, we have solved the part C, and we have solved the whole problem. I hope this was helpful to you, and I hope I see you in another lesson.